Hello everyone, I am Shay Dekel from Bar-Ilan University. I am glad to introduce our work estimating extreme 3D image rotations using cascaded attention. It is part of my PhD work together with Professor Yossi Keller and Martin Kadik, that published at CVPR2024 conference. The problem we face is estimating the 3D rotation between a pair of two given images. Our method addresses cases where there is a large overlapping, small overlapping, and non-overlapping between the two images. In the left, you can see example with small fraction of overlapping, and on the right, you can see a challenging scenario of non-overlapping at all. In that case of non-overlapping, our method has to extract cues in images, like human being, and start inferring and analyze some shapes and objects that have continuing line plane like walls and floors. 3D rotation estimation can serve in several computer vision applications, such as indoor robot navigation, where a certain robot put in place where there is non-overlapping between its current view and its offline 3D map, and the robot tries to figure out where I am. And other tasks are related to 3D reconstruction and autonomous driving. We use transformers for multiple tasks. First, we extract features using unit CNN embedding. Then, use a cross-decoding transformers for distilling inter-image information. These vectors are concatenated into vector T and insert into a transformer encoder for encoding latent space interaction between the two image pairs. Then, a cascade decoders jointly refine the cross-attention encoding T and the query rotation together. Finally, a multilayer perceptron predicts the relative quaternion rotation Q. Computing the cross-attention using a transformer encoder requires an input mask M. The mask M zeroes the self-attention terms, retaining only the cross-attention terms. In that case, only pairs of features from both images contribute to the rotation estimation, and pairs of features from the same image can't contribute to the rotation estimation. The multilayer perceptron regressor computes the quaternion output denoted as Q tilde. The training loss is formulated as relative regression loss. To evaluate our method, we use a metric of geodesic error measures. We also use position embedding in the activation maps. We assign a learned encoding to preserve the spatial information of each location. To reduce the number of parameters, two one-dimensional encoding are learned separately from x and y axes. Specifically, for an activation map, we define the sets of position embedding vector EU and EV such that spatial position ij is encoded by concatenating the two corresponding embedding vectors. EA is positional embedding of I. Any image pairs contain valuable information about overall geometric relationships. The transformer encoder can uncover these hints. The highlighted purple regions indicate explicitly or implicitly rotation-related cues, such as lines and informative analytic shapes. Visualization results of the rotation estimation. The panoramic and the crop ground truth images are marked with a green and yellow dots. The predicted footprint of one of the crop images is marked by the red dot line. The first row shows the result of the matching of images with large overlap. The second and the last rows show the matching of small overlap and non-overlapping images. Here are results on several benchmarks. We utilize the InterioNet Sun 316 and StreetLearn dataset and show the average and median geodesic errors. We also present the percentage of image pairs with relative rotation error below 10 degrees. The gray numbers indicate errors exceeding 15%. We can see that our method achieves state-of-the-art results. We also perform a cross-dataset generalization that we train our models on Manhattan datasets and tested them on the London dataset. The average geodesic error is reported. That's all for our work, and thanks for your attention.